Let's see. Let me say a few words. My name is Laurent Hodges, and I'm an associate professor of physics here at Iowa State University. And I want to talk to you today about the potential for energy conservation. I have a few references around here that you're welcome to look at afterwards if you want, and also a little bibliography, which I prepared and dittoed. And when I was at college in the Boston area, I roomed with a New Yorker who had a lot of relatives up and down the East Coast who would often visit him. And one I remember in particular was an aunt that the family generally considered to have bats in her belfry, as this woman devoted great amounts of time and energy to a succession of causes that were usually of her own invention. The first time I met her, she described to me in great detail her current concern, which was the overly cold air conditioning in supermarkets, department stores, and other commercial establishments. She claimed that the men who managed those places adjusted the temperature to a comfortable level for men in business suits and ties, making it far too cold for the more casually dressed women who did most of the shopping. She felt the practice of low air conditioning temperatures was wasteful, unhealthy, and unnecessary. Her arguments made sense to me, but when I would describe her campaign to other students, they were highly amused at the idea of a woman bugging store managers over so trivial and even ridiculous an issue. Now, that was a dozen years ago, but it's becoming fashionable for government officials to say the same thing today. And we can see that my roommate's aunt was a pioneer in an issue that combined women's rights with concern over energy resources. Fortunately, energy conservation is not such an unpopular issue today. Many periodicals have carried articles about energy conservation. A government agency has published a major report on the issue. Numerous individuals have taken steps to reduce their own energy usage, and important policies to encourage energy conservation are being discussed at the national level. My intention here today, after a few general remarks about world and U.S. energy consumption, is to discuss first the various end uses of energy and the possibilities in each case for energy conservation. Secondly, numerical estimates of energy savings that might be realized. And thirdly, some policies that might be instituted to foster energy conservation. Let me first say a few words about the world energy situation. The U.S. has about 210 million people, or under 6% of world population. And in 1970, the last year for which official UN energy statistics are available, it consumed 33% of the commercial energy consumed in the world. Commercial energy includes fossil fuels, coal, oil, gas, and electricity generated by hydro, nuclear, and geothermal power, but not such things as wood, wind power, cow dung, and so forth. This percentage has changed very little during the 1960s, although in 1950 the U.S. share of world energy consumption had been 44%. This is a remarkable fact which many people don't appreciate. While world energy consumption has risen rapidly, it has done so at an annual rate of 5% in the past decade, the U.S. share has not been decreasing. This is true of the other developed nations as well. It's easy to see who's getting the short straw. The developing nations with over 70% of the world's population saw their share of world energy consumption drop during the 1960s from 19% to 16%. While their share of world energy production was rising from 29% to 35%. I think the best summary of this situation is to be found in the Gospel according to St. Matthew, chapter 13, verse 12, where it says, "Whosoever hath, to him shall be given, and he shall have abundance. But whosoever hath not, from him shall be taken away even that he hath." When we look at per capita energy consumption, we find enormous and growing differences between the U.S. and the developing nations. In 1970, the average American consumed 27 times as much energy per capita as the average inhabitant of the developing countries, and this was up from 21 times in 1960. In fact, in recent years, the annual increases in U.S. per capita energy consumption have approximately equal total per capita consumption in the developing countries. Americans also consume about 2.5 times as much energy per capita as do those living in the other developed countries: Europe, the Soviet Union, South Africa, Israel, Japan, Australia, New Zealand, and Canada. This tremendous growth in energy has apparently not been sufficient for us, and there's a widespread feeling that we're having energy shortages. It's very hard to believe in the concept of a U.S. energy shortage in the face of the facts I just mentioned. It seems like the other countries of the world ought to be considered as having shortages. Of course, many people wouldn't mind having more energy for one reason or another, and perhaps from that point of view, we do have a shortage. By the same token, we probably should be said to have a money shortage, an automobile shortage, a housing shortage, a meat shortage, a raspberry shortage. There are a lot of people that wouldn't mind having more money, or newer cars, better housing, or more meat, or more raspberries. My topic today, however, is not whether we really need more energy. Let's accept the fact that most Americans think they do need more energy, and let's look at the alternatives. One alternative is to develop new energy sources. We're currently exploring for more oil and gas in Alaska, in offshore areas, and even in the conterminous 48 states. Not to mention foreign exploration by multinational companies which are largely owned by Americans. We're developing fast breeder reactors which make it possible to extract nuclear energy from uranium-238 and thorium-232. We're rapidly increasing funding for solar and geothermal energy. Another alternative is to import more energy from other countries. Imports of petroleum have been rising very rapidly. A few decades ago, the U.S. produced more oil than it consumed and was a net exporter of petroleum. In 1973, we've been importing about 38% of the petroleum we use. Statistics from the Oil and Gas Journal show that we are importing 32% more crude oil and petroleum products in 1973 than we did in the same period last year, that crude oil input to our refineries is up 8% since last year, and oddly enough, for a year supposedly characterized by severe gasoline shortages, motor vehicle gasoline production by refineries is up over 7% during the first 6 months. There's a great reluctance to increase our imports for monetary reasons. They worsen our balance of payments problems, and for political reasons because they provide billions of dollars to the so-called Arabs. And this would continue unless we could find a way to drive down the price of foreign petroleum, which is already much cheaper than domestic petroleum, but which some people feel ought to be a lot cheaper yet. The U.S. is also eyeing the possibility of developing the more accessible and more secure Canadian oil and gas resources consumption in the U.S., a policy which is euphemistically referred to as a continental energy policy. Still another alternative is energy conservation. Now, this is perhaps not yet a very well-defined term. Although it has been defined to include other things, I want to define energy conservation to encompass any policy or method that tends to reduce the consumption of non-renewable energy resources. Therefore, energy conservation in the space heating of homes, to choose a particular example, might encompass the following. First, the replacement of an oil or gas furnace by solar heating, since oil and gas are non-renewable energy resources, while solar radiation is a renewable resource. Secondly, the more efficient use of energy is by the replacement of electric resistance heating by an oil or gas furnace, which I'll explain in more detail later. Thirdly, the reduction of the heat needed by better insulation in the walls or ceilings of the homes. And fourth, by changes in lifestyle, such as keeping the temperature a bit lower in winter or closing off unused rooms. This third alternative, energy conservation, is my subject for today. Let me point out one reason for emphasizing it that I've not yet discussed. We now recognize that many human activities adversely affect the environment, as is in the production of environmental pollution, and that the environmental impact of major decisions by governments, industries, and individuals ought to be considered along with the economic, social, legal, and political impacts of those decisions. In fact, the National Environmental Policy Act of 1969 requires that a detailed environmental impact statement be written for every major action by a federal agency. Now, we can ask the question, how do environmental concerns affect the choices we have to solve the energy crisis? And the answer at present appears to favor the development of certain energy resources which are less polluting and the encouragement of energy conservation, since these will usually, though not always, reduce adverse environmental impacts. Let me now turn my attention to the current uses of energy in the U.S., since we need to know something about this in order to determine the value of particular energy conservation ideas. A common division of energy uses into four categories: residential, which is homes and apartments; commercial, which would be retail stores, restaurant, office buildings, and so forth; industrial; and transportation. One problem that arises immediately in determining the fraction of energy consumption by each end use is the following. About 30% of total U.S. energy consumption is by electric utilities, which generate electricity used by various other sectors. In the process of generating electricity, about 2/3 of the energy is lost as waste heat. This is the waste heat that's capable of causing thermal pollution. Should this waste heat from electric utilities, which is roughly 20% of U.S. energy consumption, or at least will be very soon, be charged to the electric utilities and included in the industrial sector, or should it be allocated to the final users of electricity, such as residences? And today I'm going to allocate it to the final users, so that any household using, for instance, 100 kilowatt hours of electricity would also be charged with the 200 kilowatt hours of waste heat produced in generating those 100 kilowatt hours. Having done so, let me indicate approximately how energy is consumed in the U.S. 40% is consumed in industry, 25% in transportation, 20% in residences, 15% in the commercial sector. Of the 40% used by industry, about 16% is for producing process steam for a great many applications, and another 11% for direct heat, such as the fuel burned in steel furnaces. About 8% is energy used for electricity for direct drive of machinery and equipment. 4% is used for non-energy purposes, lubes, grease, asphalt, feedstocks for the manufacture of chemicals, and so forth. And about 1% is used for electrolytic processes. The 25% consumed in transportation is fuel to provide motive power, gasoline, diesel oil, aviation fuel, and so forth. Practically all of this energy is in the form of petroleum products, although small amounts of natural gas, coal, and electricity are also used. It should be noted that this 25% figure includes only the energy consumed in moving passengers and freight. It does not include the energy used in manufacturing cars or building roads and airports or making parts and accessories. My own guess on the basis of some of the studies I've seen is that the total energy consumed directly or indirectly by transportation is probably something on the order of 40% of total U.S. energy consumption. Let me consider the residential and commercial sectors together. Of the 35% of U.S. energy these sectors consume, about 17% is for space heating, 4% for water heating, 3% for air conditioning, 2% for refrigeration, about 1.5% each for cooking and lighting, and the other 5% for a great variety of minor uses such as elevators and large and small appliances. All the small electrical appliances such as radios, toasters, vacuum cleaners, fans, clocks, hair dryers, etc. total roughly 1% of U.S. energy consumption. Now let me review the energy uses I've just discussed, listing them in order of importance. 25% for transportation, 17% for space heating, 16% in industrial process steam, 11% in industrial direct heat, 8% in industrial electric drive, 4% in water heating, 3% in air conditioning, 2% refrigeration, 1.5% each in cooking and lighting, and about 1% each for electrolytic processes and by small electrical appliances. From the length of this list, even without making any further subdivision into different types of transportation or different types of water heaters or different uses of direct heat by industry, we see that energy is consumed for so many purposes that any one ideal for conserving energy is likely to have only a small impact on total energy consumption. As a result, parties whose interests are adversely affected by a particular suggestion will tend to defend their interests by scoffing at the value of the suggestion. I hope we can all avoid such an attitude and conserve energy here and there in little bits, since it can add up to significant savings, as I'll discuss later. Now let's discuss the items on the list one at a time and look at some specific suggestions for energy conservation. I'll start with transportation, 25% of total U.S. energy consumption. Transportation is used to transport both people and goods, passengers and freight. The commonest forms of transportation are pipelines for fluids such as petroleum, natural gas, liquid ammonia, railroads, waterways, motor vehicles, which includes automobiles, trucks, buses, and aircraft. Pipelines transport only freight, while the others may be used for either passengers or freight. In terms of energy consumption, defined as the amount of energy required to move a given amount of freight a fixed distance, the order of decreasing consumption is the order I just used. Pipelines, railroads, waterways, trucks, airplanes. If we scale everything to railroads, defining their energy consumption on a relative scale as 1, the consumption of pipelines is about 0.7, that of waterway traffic 1, that of trucks 4.2, and that of airplanes over 60. The costs of freight transport are affected by this, of course, and in cents per ton mile we find a rather similar order. Pipelines the least expensive, followed by waterways, railroads, trucks, and airplanes. Turning our attention to passenger traffic, we find that for intercity travel, the most efficient means are buses and trains, with automobiles averaging twice and airplanes 5 times the energy consumption per passenger mile of buses. These are just approximate values, and much depending on the amount of space per passenger. For example, coach cars on trains are certainly much more efficient than sleeping cars. The location, the beginning and end of the trip, the load factors, and so forth. In urban areas, mass transit systems, which are usually buses, require only about half the energy per passenger mile of automobiles. Now we see that if we want to conserve energy, we ought to encourage certain types of transportation. Freight ought to move by pipeline when possible, or by railroad or waterway otherwise. And truck and airplane transport ought to be discouraged. Passenger traffic ought to be by existing mass transit methods whenever possible. Trucks, airplanes, and private automobiles have certain advantages with regard to speed and convenience, of course. And I don't want to imply that energy consumption is the only criterion that needs to be considered. Unfortunately, it appears that government subsidies have favored the wrong modes of transportation. Vast sums are spent on highways, which subsidize motor vehicle transportation, and efforts to oppose the highway lobby and use highway trust fund for other purposes, such as mass transit, have failed. Airplanes are also subsidized by the building of airports. Railroads, on the other hand, have received negligible assistance for many years. Railroads must build and maintain their own rights of way and even pay property taxes on them. These policies have contributed to the well-being of the big trucking firms and the desperate straits of the railroads. Let me cite another example that I consider a poor policy. The U.S. has spent several $100 million in the past decade providing operating subsidies to U.S. passenger ship with U.S. seamen, including $80 million to the SS United States before it was retired in 1969. Much of this has gone to Caribbean cruise ships, whose passengers have sometimes received a subsidy of several $100s apiece. And if you wonder what the justification is for these subsidies, the justification is national security. Now, over one-half the energy used by transportation is consumed in the private automobile, so I'd like to pay special attention to it. The Federal Register on May 2nd of this year published Environmental Protection Agency statistics on 354 light-duty 1973 model motor vehicles, largely statistics relating to exhaust pollution, but including data on fuel economy. Mileage ranged from 6.3 miles per gallon for a 4,000-pound Ferrari to 28.7 miles per gallon for a 2,000-pound Datsun. This mileage was for a particular test procedure which was intended to simulate a 7.5-mile urban trip, beginning with a cold engine. The average fuel consumption varies linearly with weight, so a 4,000-pound car averages half the fuel economy of a 2,000-pound car. However, there are wide variations even in a given weight class. For example, the 39 vehicles in the 3,500-pound class exhibited fuel economies ranging from 7.6 miles per gallon for a Jaguar to 20.3 miles per gallon for a Volvo, which is a range of a factor of 2.7. It's clear that there's a great opportunity for conserving energy by purchasing lighter weight vehicles and by purchasing the more efficient engines. In addition, certain accessories on automobiles can consume significant amounts of energy, particularly air conditioners and automatic transmissions. I should interject at this point the comment that my own analysis of the fuel economies of the 1973 cars shows that there's generally very little difference in fuel economies between vehicles which are identical, except that one of them has a manual transmission and one of them has an automatic transmission. Out of 23 such cases listed in the Federal Register, the automatic transmission had a lower fuel economy in 12 cases, but a higher fuel economy in 11 cases, so you can't always count on that particular aspect. Another factor affecting fuel economy in automobiles is the presence of exhaust emission controls required by the Federal Clean Air Act. The Environmental Protection Agency has estimated that these controls reduced fuel economy in 1973 cars compared to cars in the 1957 to 1967 period by about 6%. But the same EPA estimates indicate that the 1972 and 1973 cars have better average fuel economy than the 1968 and 1971 cars. There is general agreement that the approach to emission controls being undertaken by the U.S. auto manufacturers, which is the use of oxidizing catalysts for carbon monoxide and hydrocarbons and reducing catalysts for nitrogen oxides, will lead to fuel economy penalties compared to the 1971 cars, 5 to 15% for large cars and up to 20 to 30% for small cars, when the strict requirements of the Clean Air Act amendments in 1970 are finally met. Now, there's no fundamental reason why pollution control should reduce fuel economy. And indeed, the emissions of carbon monoxide and hydrocarbon pollutants are actually due to incomplete fuel combustion, which means incomplete extraction of the energy in the fuel. The recently postponed 1975 limits on carbon monoxide and hydrocarbons, which the U.S. auto manufacturers had consistently claimed they could not meet, have been met by 3 engines: a Mazda rotary engine, which has a large fuel economy penalty, a Mercedes diesel engine, which has better fuel economy than uncontrolled U.S. cars, and a Honda stratified charge engine. The stratified charge engine is very similar to the ordinary internal combustion engine. It has a conventional engine block, pistons, and spark plug, but the cylinder head, intake, and exhaust manifolds and the carburetor are modified. The engine has a pre-chamber and 2 carburetors, one for a fuel-rich mixture and one for a fuel-lean mixture. At present, the stratified charge engine appears to be the best bet as the answer to our automotive pollution and fuel economy problems, and has received the official blessing of the Committee on Motor Vehicle Emissions in the National Academy of Sciences. It has the lowest bare engine emissions, it is more durable, it requires less maintenance, and it is comparatively inexpensive. It also has no fuel economy penalty compared to uncontrolled cars with standard internal combustion engines, which is of primary importance to our discussion today of energy conservation. The stratified charge engine is a very old engine. In looking through old transactions of the Society of Automotive Engineers, I discovered a 1922 paper which enthusiastically extolled the stratified charge engine, which was the name by which it was known even then. In 1968, the same journal contained a long, enthusiastic article about the engine by Ford Motor Company engineers who discovered that on a luxury car with 430 cubic inch displacement engine, the stratified charge engine had a 30% better fuel economy than a standard internal combustion engine of the same size. It's been estimated that meeting the exhaust emission requirements of the Clean Air Act amendments will cost new car owners a little over $300 over a 5-year period compared to cars with 1970 controls if the stratified charge engine is used, but over $1,000 extra for the 5-year period if the dual catalyst is used. To summarize this discussion, there's no reason why exhaust emission controls should reduce fuel economy. Two methods, the stratified charge engine and the diesel engine, may well increase fuel economy compared to uncontrolled cars from the 1960s. Now, there are many steps that an individual driver can take to improve fuel economy and thereby conserve energy. And many of these have appeared recently in oil company ads and elsewhere. For example, first, pacing the driving to minimize stops, which saves brakes as well as gasoline. It always surprises me how many drivers keep their foot on the accelerator when there's a red light or stop sign ahead and brake to stop instead of slowing down. Secondly, keeping the tires properly inflated, because underinflated tires have greater rolling friction and require more engine power. Thirdly, keeping the engine properly tuned. An out-of-tune engine wastes fuel and produces more air pollution too. Fourth, avoiding fast getaways. Fifth, turning the engine off rather than letting it idle when it stops for a few minutes. Sixth, using the brake rather than the accelerator to hold the car in place on an incline. And seventh, driving at slower speeds. Maximum fuel economy occurs at rather low speeds. The same Ford Motor Company tests on the 430 cubic inch displacement engine in the range of 30 to 70 miles per hour showed the best mileage at 30 miles per hour. Compared to 30 miles per hour, it required 5% more fuel to go a given distance at 40 miles per hour. It required 13% more at 50 miles an hour, 23% more at 60 miles an hour, and 38% more at 70 miles per hour. And similar statistics have appeared elsewhere. Some of you may have remembered seeing the recent front page article in the Des Moines Sun-Times Register about the reporter with a small sports car who was surprised at discovering how much better his mileage was on the interstate going 50 miles an hour than it was at 75 miles an hour. In addition to using small cars with few power-consuming accessories, in instituting good driving habits, energy consumption could be reduced by driving less, by using carpools to work or shopping centers or recreation areas, by combining trips to different places, by walking or bicycling or even motorcycling more, and by living close to work. My own experience is that gasoline consumption drops dramatically when you move close enough to work to walk in daily. In this connection, I note that some government agencies hit by sharply rising gasoline prices are requesting their employees to ask themselves constantly, is this trip necessary? An old World War II slogan. And next, I'd like to discuss space heating, which accounts for about 17% of U.S. energy consumption. Now, the purpose of space heating is to maintain a comfortable indoor temperature, say 65 to 70 degrees Fahrenheit, during periods when the outdoor temperature is much lower. So most of that requirement for space heating occurs in winter. Anytime a building is warm inside and cold outside, heat is going to flow from the inside to the outside. This heat loss has to be made up by some source of heat, which is usually a gas or oil furnace or electric resistance heating, in order to maintain the inside temperature. The amount of heat lost measured in BTUs per hour or kilowatts is approximately proportional to the temperature difference, proportional to the thermal conductivity of the intervening materials, and inversely proportional to the distance between the inside and the outside surfaces. The key to reducing heat loss is to have good insulation, in other words, to have walls and ceilings containing material of low thermal conductivity. In addition, thicker walls and ceilings will help. There's been a lot of interest in recent years in the use of better insulation, and the studies that have been made indicate that very substantial savings, often up to 50%, are possible by the use of increased insulation. A new home which incorporates more insulation than is standard will have a higher initial cost, but even at present prices for fuel, the overall cost over a period of years will be less. So skimping on insulation is a clear case of penny wise, pound foolish. The Federal Housing Administration has in recent years increased the insulation requirements of its minimum property standards, which apply to all FHA-insured homes, by lowering the permissible heat losses by a factor of 2. In a 1971 Oak Ridge study by John Moyers shows that still larger savings are possible without an economic penalty. If fuel prices continue to rise faster than insulation prices, even more insulation may become economically justifiable. Now, important heat losses can occur through windows and doors. The thicker the glass in a window, the lower the heat losses. It's even better to use 2 panes of glass with intervening dead air space, as in double pane windows or windows with storm windows. For example, a piece of glass a millimeter thick has half the heat loss of glass half a millimeter thick, but 36 times the heat loss of 2 pieces of glass, each 1 millimeter thick, separated by a millimeter of air. Storm windows and doors are a very good method of conserving energy, but not those of aluminum, since a given thickness of aluminum will have about 2,500 times the heat loss of an equivalent thickness of wood. In addition to reducing heat losses by insulation and storm windows, there are a number of other steps that can be taken to avoid cold air infiltration in the house, such as weather stripping or caulking around windows and doors, keeping the fireplace dampers closed when the fireplace is not in use, and opening doors for the shortest possible time. Another important consideration is the efficiency of the furnace or other source of heat. One method of conserving energy is to maintain furnaces to ensure high efficiency by keeping heat exchanger surfaces clean, by replacing dirty air filters, and so forth, in addition to ensuring that the register openings are not blocked inside the building and that the system is properly balanced so all rooms have the desired temperature. Gas and oil furnaces are typically 60 to 85% efficient, the rest of the heat being lost in the stack with the combustion products. Electric resistance heating is nominally 100% efficient. In other words, all the heat produced remains in the building. But as we discussed a little earlier, the generation of electricity is only about 1/3 efficient. So the overall efficiency of electric resistance heating is only about 1/3. This means that it takes about twice as much gas or oil to heat a home when it's burned at the power plant and then transmitted to the home in the form of electricity, as it does to use the gas or oil directly in a home furnace. If you add in the cost of generating and transmitting electricity, it becomes surprising that anyone can afford electric resistance heating. Of course, the cost is reasonable only in a very well-insulated home, and even then a gas or oil furnace would still conserve energy. There is one interesting concept for improving the efficiency of electric heating, and that's the heat pump. A heat pump is conceptually identical to a refrigerator, which extracts energy from a cold region, namely the inside of the refrigerator, and disposes of it in a warm region, which is usually the kitchen. Except that in a heat pump, the outside air or the ground is the cold region, and the inside of the house is the warm region. Heat pumps offer the possibilities of efficiencies greater than 100%, since more heat can be transferred than energy is used in transferring it. Heat pumps with 200% efficiency exist and are used in some large commercial establishment, but their cost, their durability, and the fact that they work less efficiently at colder temperatures when you need them make them unsuitable for home use in many cases. With a high-efficiency electric heat pump, the overall efficiency of converting fuel into space heat would be comparable to our gas or oil furnace. Of course, maybe it will have certain advantages. There are some methods of conserving energy in space heating which would require at least some changes in lifestyle. Keeping the thermostat lower in winter and then perhaps wearing light sweaters instead of short sleeves. will reduce the thermal gradient between the inside and the outside and thereby reduce heat losses. It's good practice, of course, to turn the thermostat far down, say to 55 degrees Fahrenheit, when no one is in the building for a lengthy period of time. There's also been renewed interest in the use of solar energy. Solar radiation incident on a typical resident is sufficient for heating and cooling the residence, and therefore offers an excellent possibility of reducing the depletion of non-renewable fossil fuels. And by contrast, I might mention that the solar energy incident on a motor vehicle is far too little to power a motor vehicle. There are several solar homes in the U.S. today, and engineers who have studied the concept feel that economical and reliable solar heating could become a reality within a few years if the research and development funds are forthcoming from some source. Solar heating is used in some places, such as Florida, for hot water heating, and could be used in many other places, and this would reduce fossil fuel usage by a few %. With regard to water heating, it's often been noticed that the energy in hot water is generally lost as soon as it is used and sent down the drain, and there may be ways of recapturing some of it, say by heat exchangers on drains. Energy consumption in water heating, which is 4% of total U.S. energy consumption, which means it's actually more than air conditioning, can also be reduced by using gas rather than electric heaters, by repairing leaky hot water faucets quickly, by using cold water wash whenever possible, by using a shower rather than a bathtub and keeping showers short, and by turning the water heater off or down during vacations. Now, let me say a few words about air conditioning at this point. Air conditioning is really space cooling, and many of the energy conservation ideas for space heating are applicable to space cooling. Better insulation, including storm windows and doors, will prove helpful, as will the control of air infiltration into the cooled home. Higher indoor summer temperatures, the objective of the woman I mentioned at the beginning of my talk, will also help. It's obviously ridiculous to maintain indoor summer temperatures that are lower than indoor winter temperatures. There's some new types of windows that aid in reducing the air conditioning load. Several firms make reflecting glass to keep out much of the solar radiation. One type, for example, is glass with an aluminized laminated polyester film on the inside surface, which reflects practically all the ultraviolet and infrared radiation and some of the visible light. Large multi-glass windows with reflecting glass have a very interesting appearance. Some of you may have seen them in large cities sometimes, and I personally find them very pleasing in appearance. There are less sophisticated ways to keep sunlight out in summer by drawing draperies, especially white ones, by using awnings or outside shutters or louvers, etc. In winter, the opposite effect is desired, and the windows facing the sun ought to be allowed to let sunlight in. Although drawing the drapery shut elsewhere will provide extra dead air space and reduce heat losses on those windows. An excellent idea is to grow deciduous trees or shrubs just outside the windows. In summertime, the foliage will shade the window, but in winter, when the foliage is absent, the sunlight can enter. It's also well known that air conditioning loads are reduced if the attic is cooled by good ventilation, and so it's worthwhile to have an attic fan for that purpose in summertime. Finally, in order to conserve energy, one ought to use only the more efficient air conditioners. The efficiency of an air conditioner can be measured by dividing the cooling capacity by the electrical power required to operate the air conditioner, usually under specific conditions of humidity and outside temperature. Cooling capacity is generally measured in BTUs per hour and electrical power in watts, although they're fundamentally the same unit. This information is often found in manufacturer's brochures, such as this one here from Sears. Now, this brochure actually lists the efficiency in a column headed BTUs per watt. That really ought to be BTUs per watt hour. And this number ranges from 5.2 for a 6,000 BTU per hour unit drawing 1,150 watts to 10.1 for a 14,000 BTU per hour unit drawing 1,380 watts. Note that the latter unit furnishes 2.3 times as much cooling capacity for only 1.2 times as much electric power. If you accumulate brochures on room air conditioners from a number of dealers, you'll find efficiencies ranging from below 5 BTUs per watt hour to above 12 BTUs per watt hour. The more efficient units usually require 115 volt lines, while the less efficient units are usually for 230 volt lines, although there's no fundamental reason why this should be the case. The more efficient units usually cost more, but they'll pay for themselves in only a few years, even in this part of the country. So you should pay close attention to this when you purchase an air conditioner, and ask dealers, as I have done, to try to advertise their efficiencies. There also have been suggestions that dealers install some kind of markings on the air conditioners giving the efficiencies for purposes of comparison by shoppers. Now, let me make one more point relative to air conditioning. Electric power eventually becomes heat, so the use of electric lights and appliances increases the air conditioning requirements. 1,000 BTUs per hour equals 293 watts. So this means that just 250 watt light bulbs or one 300 watt television set will increase the cooling requirements of a room by 1,000 BTUs per hour, which is not an insignificant amount. Now, a few minutes ago, you may have wondered whether or not reflective glass windows on large commercial buildings is such a good idea in wintertime, and you'd like to let the sunlight in. The fact of the matter is that even in winter, some office buildings have to be air conditioned, at least the inner parts have to be air conditioned, just because of the heat generated by lights, appliances, and people. One person is 175 watts, or about 600 BTUs per hour. The new Westinghouse Nuclear Center at Monroeville, Pennsylvania obtains all of its heating from an automatic heat of light recovery system combined with excellent insulation. I should mention parenthetically that the larger a building of a given shape is, the lower its skin area to volume ratio, so that large buildings generally require less heating per usable volume. This suggests that the single-family home is basically of inefficient design as far as space heating and cooling are concerned. I'd like at this point to make a few more comments about lighting. Lighting uses about 1.5% of the energy consumed in the U.S. This figure could be reduced by greater use of fluorescent lights in place of incandescent lights, as the former are typically about 4 times as efficient as the latter. Sometimes you can try to compare the light from a 40-watt fluorescent bulb with a light from a 150-watt incandescent bulb. A 40-watt fluorescent bulb produces about 8 watts as usable light, measured in lumens, and 32 watts of heat. And the light eventually also becomes heat, as I mentioned a moment ago. A 100-watt incandescent bulb, however, produces only 5 watts of usable light and 95 watts of heat. Incandescent bulbs themselves differ somewhat in their lumen-to-watt ratios, and the Durotest company has a new line of watt-saver bulbs which use krypton gas and which have a lumen-to-watt ratio about 10% greater than that of ordinary incandescent bulbs. One way to reduce energy requirements for lighting would be to reduce the illumination levels. And I'm sure you're all aware that most buildings have far greater illumination than is required. It's particularly interesting to compare the recommended illumination levels of the U.S. and the British illuminating engineering societies. The U.S. standards exceed the British, sometimes by as much as a factor of 3, even though the two sets of standards are apparently based on essentially identical experimental data. The U.S. Illuminating Engineering Society has come under strong criticism for many years for its high recommended illumination levels, which in some cases have been revised upward several times over the years, and which critics claim are designed to benefit the companies that employ most of the members of the Illuminating Engineering Society. If we turn our attention to appliances, we find that many ideas already mentioned are applicable. Less energy is generally consumed by gas appliances than by electric appliances, as for example in stoves and clothes dryers. Pilot lights consume appreciable amounts of gas, but they're not necessary. We don't need to go back to using matches because there are electronic igniters. Our gas dryer, for example, has no pilot light. Just as air conditioners differ in efficiency, so do many electrical appliances. The use of solid-state circuitry in radios, televisions, and calculators generally reduces power requirements. A pocket calculator may use less than 1% as much energy as a comparable desk calculator. Philco recently announced a new line of refrigerators and freezers requiring 30% less energy than competing models. And there's one firm that makes very heavily insulated ovens which retain heat and thereby require less energy. A good design is important here. Refrigerators in recent years have had thinner walls to make more usable space inside. And from our discussion of heat losses a few minutes ago, we recognize that this means greater heat losses. This has been partly avoided by the use of better insulating materials. The newer refrigerators can be colder on the outside surface, which leads to condensation problems when the humidity is high. As a result, most models have electric heaters just inside the outside surface of the refrigerator doors, which of course increases the energy consumption. And this is not just a wild story, but it's actually the truth. One refrigerator has an electrosaver switch. If you wonder what that is, when the humidity is low, you're supposed to turn it on, and all it does is save energy by turning the electric heater in the door off. Now, small electric appliances account for only about 1% of U.S. energy consumption. This could probably be reduced by more efficient designs in some cases and by people doing without in others. But there are probably more important things to be concerned with when we're talking about energy conservation. Let me just describe to you a couple of devices that you may not have heard about. One, there's a machine with an electric eye that measures the diameter of asparagus stalks and cuts those that are large enough. This was in a recent Des Moines Sunday Register article. Another one I read about is a photoelectric device combined with a tie rack that eyes the color combinations of a man's clothes and selects the appropriate tie to go with his outfit. That one costs a few $100s. Turning our attention to the industrial sector, which consumes 4% of our energy, there are many processes which are being made more efficient each year, and an emphasis on energy conservation will probably lead to many others. Unfortunately, there's very little information about industrial energy consumption in different types of industries, and therefore little information about how energy could be conserved. There appears to be general agreement that fuel costs and therefore fuel consumption have been of minimal concern to industry in the past, and that there is room for considerable improvement. Charles Berg, Director of Engineering at the Commerce Department's Institute for Applied Technology, thinks that 30% fuel savings could be accomplished today in industry at no economic penalty. A few examples of progress can be cited. Large amounts of electricity are used in the production of aluminum, but the amounts have been reduced by improvements in the electrolytic reduction of aluminum. A recent Alcoa press release described a new process which required still less energy. Dow Chemical recently discovered a way to reduce energy consumption 20% at its Midland, Michigan latex manufacturing facility. Union Carbide reports that its chemicals and plastics group has decreased energy consumption 6% in the last 3 years, while overall production increased. And for a number of years, the energy consumed by the steel industry in the production of a ton of steel has been decreasing as the basic oxygen furnace replaces the open hearth furnace. However, if we include the energy used in preceding steps, such as coke making and iron making, the open hearth and basic oxygen furnaces have rather similar energy consumption per ton of steel. The electric furnace using scrap metal exhibits particularly low energy consumption, even when the waste heat produced in the generation of electricity is included. This last fact points up an excellent way to reduce industrial energy consumption, just to recycle more. Recycling metals from scrap generally consumes much less energy per unit mass than extracting them from the ores. Studies have shown this for iron, aluminum, copper, titanium, and other metals. Recycling will become more important as the better grade ores are exhausted, since extraction of metals from low grade ores requires more energy. With regard to beverage containers, Bruce Hannon has calculated the energy consumption and discovered that recycling glass consumes more energy than manufacturing it from the raw materials. On the other hand, returnable bottles consume much less energy than throwaways, whether bottles or cans. Throwaways generally require 3 to 4 times as much energy per gallon of soft drinks. Let me now mention a few more general methods of conserving energy, not tied to any particular sector. Since the efficiency of generation of electricity from fossil fuels or nuclear fission is only about 1/3, large savings would be possible if the efficiency could be increased. There must always be some waste heat according to the second law of thermodynamics. Efficiencies, however, have increased from around 8% in 1900, which means that during the 20th century, the ratio of waste heat to electricity has been reduced from about 12 to 2. The best new fossil fuel plants have efficiencies around 40%, while the typical light water reactor nuclear plants have about 33% efficiency. Newer types of nuclear plants, such as the high-temperature, gas-cooled, and fast breeder reactors, will have efficiencies comparable to those of the most efficient fossil fuel plants. And now, what are the possibilities for even greater efficiencies? There are a number of them, and several of them might lead to efficiencies of 50 to 60%. For example, combined cycles involving gas and steam turbines together, magnetohydrodynamics, potassium topping cycles. Now, these are all ideas worth pursuing in further research. Controlled thermonuclear fusion, if it ever proves successful, may also have high efficiencies. The importance of higher efficiencies can be seen from the fact that an average efficiency of 50% would mean waste heat equal to the electricity generated instead of twice as much as is the case today. It's also possible to use new fuels, and in several places fossil fuel furnaces and electric power plants are being adapted to burn municipal solid waste. Ames is planning to do this within the next couple of years, adapting its boilers to handle shredded combustible solid waste that would otherwise go to the city landfill. The use of solid waste for this purpose will conserve fossil fuels and solve at least part of the solid waste disposal problem, all at reasonable cost, although it may impede progress towards recycling of paper and paperboard and other combustible solid waste. Fossil fuel could be conserved if greater use were made of waste, including organic waste, but it appears as though waste as a group will be a minor fuel source at best. A better bet is solar energy, and some new ideas for generating electricity from solar radiation have been proposed in recent years. There remain important problems with the collection and the storage of energy from the sun, and this is an area which I think deserves much greater funding. Another possibility is to make use of the waste heat. A number of concepts exist that might provide substantial energy savings. One is district heating, in which a power plant produces electricity, space heating, and space cooling for a number of buildings close together so that the waste heat is not completely wasted. This is exactly what the physical plant at Iowa State University does, for example. I've been told it was done many years ago in downtown Ames before cheap natural gas became available. A similar concept being promoted by the natural gas industry is the total energy concept for shopping centers, large apartment buildings, hospitals, and similar complexes. In these, natural gas is used in gas turbines or gas engines to generate electricity, and the waste heat is used for space heating and space cooling. Even though the small electric generating station has perhaps only 25% efficiency, the overall efficiency of the total energy installation may be 65 to 85%. Another major saving of energy would result from greater emphasis on durability. If machinery and appliances and motor vehicles lasted longer and needed fewer repairs, there would be significant savings in the industrial and transportation sectors due to decreased requirements of manufacturing and transport of these items. It's long been recognized that planned obsolescence involves enormous social costs, and the wasting of energy is one of those. And I personally think more social responsibility in this area could be had from the advertising and industrial design professions. When all is said and done, how much saving of energy would be possible? Let's first suppose that we estimate the possible savings if we continue to gain all the current benefits we enjoy from the consumption of energy without changes in lifestyle. Today, about 50% of our energy consumption is wasted. In other words, it doesn't do useful work. The laws of thermodynamics tell us this can't be reduced to zero. It might even be possible to save more than 50% of our fossil fuel usage if we also shift to more efficient transportation modes, make greater use of solar energy, etc. Referring to actual numbers from some existing studies, such as those in the bibliography, we might save some 12% of total U.S. energy consumption by improvements in the industrial sector, 7% by better insulation in buildings, 1% by more efficient air conditioning, 5% in transportation, all with the present technology and at currently economically justifiable costs. Now, that adds up to 25% right there, which would be sufficient to make oil imports unnecessary and reduce domestic fuel consumption substantially. It couldn't be done all at once, of course, but the 1972 report on the potential for energy conservation in the Office of Emergency Preparedness calculates attainable savings at 16% by 1980 and even more thereafter. If we permit changes in lifestyle, even greater savings would be possible. By changes in lifestyle, I don't mean going back to the Dark Ages. If we suddenly reduced our energy supplies and therefore our energy consumption by 1/3, an amount that certain groups claim would return us to the Dark Ages, we would only be returning to the average per capita levels of 1960, when life was not all that nasty, short, and brutish. And if we reduced it by 60%, we would be on a par with Europe and the other developed nations of the world, where life is not all that nasty, short, and brutish either. Rather, by changes in lifestyle, I mean the use of smaller, lighter cars, increased reliance on mass transit, fewer single-family homes and more housing complexes or communal living arrangements, cooler indoor winter temperatures and warmer indoor summer temperatures, more separation of solid waste to facilitate recycling, more walking and bicycling, beverage purchases only in returnable bottles, greater use of carpools, etc. These are mostly mild changes, although some people have violent objections to some of them. Even more drastic changes are possible, of course, such as those of the back to nature movements. In the Midwest and West, there seems to be a general distaste for the idea of mass transit. But those of us who have lived in metropolitan areas with good public transportation know that it can be cheaper, faster, and even more pleasant than driving one's own car, although perhaps slightly less convenient at times. I lived in the Boston area for a number of years and made extensive use of the MTA even when I had my own car. There's been talk in Ames, I noticed, of spending several $100,000 to expand the airport. From the point of view of energy conservation, perhaps decent public transportation in the community would be better. And now, what policies can be instituted to encourage energy conservation? Now, let me list some. First, public education to increase awareness of energy losses and the potential for energy conservation. And that's my purpose here today. Secondly, increased energy prices, such as through higher taxes on energy. This would encourage energy conservation while leaving it up to the private sector to discover and implement the best methods of doing so. Third, the use of level or rising rate structures for electricity and gas. Does it really make sense in this day and age to penalize the small consumer by charging him or her more per kilowatt hour of electricity or cubic foot of natural gas than the large consumer? Right here in Ames, the residential natural gas rates decreased by more than a factor of 3, and electric rates decreased by more than a factor of 4 from small to large residential users. Ames also has special rates to encourage the use of electric space heating and water heating when they ought to be discouraged. Fourth, subsidies and tax breaks to encourage energy conservation, such as tax breaks to owners of older homes who upgrade their insulation, which can be an expensive process, subsidies to railroads and mass transit construction of bicycle paths. Fifth, reducing or abolishing subsidies and tax breaks which encourage energy consumption. Now, let me give you a few examples. Oil depletion allowances tend to reduce energy prices. Railroad freight rate differentials between virgin resources and scrap discourage recycling. This is an issue which is now in the courts. Highway and airport subsidies encourage those less efficient modes of transportation. Sixth, legislation against certain energy inefficient practices. We could forbid the sale of air conditioners of less than a particular efficiency. We could institute stricter building codes with regard to insulation and window glass. We could minimize the promotional advertising by energy utilities. And we could set lower limits to the fuel economies of motor vehicles in given weight classes. A seventh policy would be to institute financial penalties against energy consumptive practices. For example, it's been suggested that there be special levies on low fuel economy vehicles. Or we could charge larger tolls for cars with only 1 or 2 people in them, like the Oakland Bay Bridge does. Eighth, we could fund research and development into promising energy conservation methods. I think solar energy and certain forms of mass transit are good possibilities. Any given energy conservation idea can be encouraged by one or more of these methods. In accordance with the provisions of the National Environmental Policy Act with regard to natural resources, we should always consider the energy consumption impact of all major government actions. For example, mass transit may lead to energy savings, but not necessarily, since some of the new ideas for fast mass transit are very inefficient as regards energy consumption. Needless to say, each policy needs to be carefully assessed with regard to possible undesirable effects on the environment, on the economy, on certain groups of people, and so forth. The best way to do this would be to begin a national debate on policies to encourage energy conservation and thoroughly air out each issue. Now, what can each of us do? Let me make 3 suggestions. First, we can educate ourselves and others with regard to energy conservation. Secondly, we can work through the political system for policies that tend to encourage energy conservation. Third, we can stress energy conservation in our own lives. In particular, we might look at our home insulation, the efficiency of the appliances we purchase, and at our transportation habits. In conclusion, let me state that I do not regard the energy crisis as the most important problem that we face. I think it ranks behind such problems as the threat of nuclear catastrophe, the dominance of the military-industrial complex, environmental pollution, the threats to freedom of the press and to privacy, and the existence of poverty, hunger, racism, and sexism. But we need to work on all of these problems simultaneously. And it seems to me that energy conservation is the most attractive and significant solution to the current concern about the shortages and environmental effects of energy, to the feeling of many people at least that we can fuel some of the people all of the time and all of the people some of the time, but that we can't fuel all of the people all of the time. Thank you.